All right, folks, Bass Action is back in action here. On this page of notes, we are going to investigate 3 new ideas related to graphs, information we can obtain from our graphs. We are going to look at intervals that we will describe as increasing, decreasing, or constant. We will look at graphs and get an understanding whether they're continuous or discontinuous. And we will also look at the idea of local max and min versus an absolute max and min. So we're going to first jump into here, increasing intervals. An increasing interval is going to be an open interval of x values. Now that means that it's going to use curved parentheses because we won't include endpoints, and it will be x values where f of x sub 1 is less than f of x sub 2. Now that might initially seem confusing, but what that's telling us is that the y coordinate on the left, our first one, is going to be lower than the y coordinate on the right. That's all that f of x sub 1 and f of x sub 2 is talking about. So if we go ahead and we take a look at our graph here at the bottom, and we read our graph from left to right, what we can see is that as we're reading from left to right, we can see that our graph is going up in that interval, and it's going up in this interval. Now, a couple things that we can add to this graph. First of all, when a graph hits the edge of our grid, we can assume that there's actually an arrow on the end and an arrow on the end here, meaning it's going to continue beyond the edge of the grid. When we're talking about our increasing, decreasing, or constant intervals, our increasing question here is question E. What we are going to look at is this behavior, as you can see I've highlighted, this behavior of the graph, the y values, but our answer is actually going to be the x values where that behavior actually occurred. So our answer is x values, even though we find it by looking at the y values. So our answer for our increasing interval here is going to be negative infinity. And what we're doing is we're following the x values where this highlighted interval happens. And we can see that the last x value where the increase in interval happened was at a negative 2. So it's going to be negative 2. And as it described up above, these intervals need to be open. So I'm going to put a parenthesis there, not a square bracket. Now I've highlighted another interval where the behavior of the graph appears to be increasing. So I'm going to do a union here. And again, I can observe this y behavior, but I want to describe the x behavior. So I can see that the first x value where this new interval starts is 5, and it's going to continue all the way to positive infinity. So my other increasing interval is 5 to positive infinity, and they all have to be open intervals. Now we can go back up here and we can look at our decreasing intervals. Our decreasing intervals will also be open intervals. So of course, those are also going to have open parentheses, those curves. They're going to be x values. So we're going to describe the interval with an interval of x values. But this time we're looking for where the f of x sub 1 is more than the f of x sub 2. What that means is that we are looking for places where the initial y value is higher than the second y value. So if we go down here to our graph, what we can see is we read this graph from left to right. I can see that I'm going up. This is our clue for the next one. It's going constant. If this graph had actually been connected here, this would have been a good decreasing interval, but it's not. So then we just jumped to our other increasing interval. So what we can say here for our decreasing interval question is that there are none. There are no intervals on this graph where the behavior of the graph is decreasing or falling. Our constant intervals will also be open intervals of x values again, But now we're going to look for where the y values remain constant. So f of x sub 1 is going to equal f of x sub 2. So now we're going to be looking for it to remain constant and flat. And I already gave a clue to that when we looked down here below. So we could see before that we had this nice flat spot right here, this plateau. So I can highlight that as my constant interval, and I can answer that question here. So of course that needs to be a open interval. I'm going to look at the x values that described that y behavior. This interval starts at an x value of -2, and it continues to an x value of 2. So we're going to describe that interval as a -2 to 2. Again, we never include those endpoints. The endpoints are considered neutral. It's where it transitions from one behavior to the next. Now, moving back on up, we're going to talk about continuity. So on our second section, we're going to talk about continuous versus discontinuous. So looking along here, we can see that we do need calculus in order to get a precise definition for our continuity. However, we can do this from an easy just observation technique, and we can find that a function is continuous if the graph has no gaps. Okay, so if there are no gaps. Now, the easy way to think about this is that if we can trace the graph without lifting the pencil from the paper. So if we go to our graph here at the bottom and we try to trace this graph, I can follow the path of my graph, and in order for me to get to that other interval, I have to lift up my pencil to continue my tracing, which would mean that this graph is not continuous. So that's question A. Is the function continuous? No, it is not. We had to lift up our pencil. We can actually answer the domain for this function as before we go up and we talk about our max and our min. Our domain for this function, remember, the domain is going to be the collection of all of our x values. So remember, we're looking for x values here. So if we wanted to find our x values, what we would want to do is trace our graph. We would imagine moving along this x axis and determining, are there points within this x interval? And I can see that there are, with the exception of this small gap here where we lost our continuity, and then it starts again. So we can describe our domain here as -2, or negative infinity, I meant to say there. Sorry about that, let me erase. Negative infinity, I got ahead of myself on my interval. So negative infinity to a -2. Now with our domain, we can use our brackets. Increasing, decreasing, constant are open. They have neutral turning points, but domain lists the actual x values. So I have my initial domain, then I'm going to restart it at 5 to positive infinity. And just to reiterate that, I skipped the interval here from 2 to 5, and I just noticed that I should have had a positive 2 there. Let's make that a positive. Didn't mean to write that negative. Sorry about that. Now the last thing that we need to talk about is max and min. These can get a little bit confusing for students, so let's go up here and look at our max and min. So our max and min are going to occur at a single point. Okay, so a max and a min have to be a single point. You can't have an entire interval that we consider a max or a min. Okay, so an interval cannot be a max or min, even if it looks like there's a big high plateau. Now let's first talk about local max and min. So our local max and min always require an increasing or decreasing change. Okay, so the graph has to change from either increasing to decreasing or decreasing to increasing. Okay, they will always appear as what we can think of as a peak or a valley on the graph. It has to go from increasing to decreasing. So if we are looking at our graph that we have down here below, tracing our graph, I can see that I'm going to go up and I'm going to go from increasing to constant. So that doesn't count because it has to be increasing to decreasing. And then I just restart all over again. So this graph doesn't have any local max or mins. So there are none. So we have no local, there's no local max, there's no local min. Now, when we want to talk about our absolute max and min, so let's talk about those. So when we talk about absolute max and min, those, however, do not require an increasing or decreasing change, okay? Thus, those can be what we will call the closed endpoints of an interval, okay? And they can be considered a max or min. So they can simply just be a high point. They don't have to be where it switches from a high to or increasing to a decreasing. Later, we will talk about holes. A hole cannot be a max or min because a hole is not truly on the graph, we will find. And when we write our max and min, we are going to write those as an f of x, in other words, a y value, at a particular x value. So let's take a look at our graph down here below. We're just about done. So when we take a look at our graph down below, this graph is going to continue forever in this direction, so that's not going to give us an absolute min there. And then I'm going to go up, I'm going to be flat, I'm going to have a low spot, and then I'm going to continue up. Our temptation is to want to call this point here an absolute min, but this cannot be our absolute min because our graph actually continues forever on down. Now, when we get into class, I'm going to show you some more examples that allow us to write these a little bit more. So, because this particular example does not then have an absolute max or an absolute min, because this graph is continuing forever up and down. When we get into class, we will do some more examples that will actually show these graphs. So we're going to investigate that idea more. For right now, the big ideas I wanted you to get from these graphs were the writing these increasing, decreasing intervals, thinking about this graph in terms of continuity, and then the max and min we will explore more in class. All right, let me know if you've got any other questions and we'll extend it in class.